Welcome to today's paper reading. Today's paper is titled, Decoupling Common and Unique Representations for Multimodal Self-supervised Learning. This paper was published on AR14 by Wang and colleagues from Technical University of Munich and German Aerospace Center. The abstract highlights the limitations of current multimodal self-supervised learning approaches, which primarily focus on common representations across modalities but neglect intramodal training and unique representations specific to each modality. To address these issues, the authors introduced DeCUR, a method that distinguishes between inter- and intramodal embeddings through multimodal redundancy reduction. This approach aims to integrate complementary information from different modalities. The effectiveness of DeCUR is demonstrated across three multimodal scenarios, showing consistent improvements regardless of the architecture used and in settings where modalities are missing. The authors hope that this work will provide valuable insights and encourage further research into the hidden relationships within multimodal representations. The research aims to solve problem X by investigating Y. The research focuses on Z and its impact on A. Understanding problem X is essential to advancing the field of Y. Previous research has shown B, highlighting the need for further investigation of Z. In the realm of self-supervised learning, several methods have been explored. Generative methods like autoencoder and masked autoencoder reconstruct data from partial information. Predictive methods, such as predicting rotation angles, aim to understand data transformations. Contrastive methods, including CPC, SimCLR, and MoCo, train joint embedding architectures using negative samples. Multimodal self-supervised learning extends contrastive learning to scenarios with multiple modalities, exemplified by CLIP for language image and VTT for video-audio text. DeCUR, our proposed method, extends Barlow twins by decoupling common and unique information without relying on negative samples. Modality decoupling, though less explored in self-supervised learning, has shown benefits in supervised settings, such as in RGBD scene recognition and audio-visual learning, where balancing and controlling the optimization of each modality is crucial. Figure 1 illustrates the separation of common and unique representations across two modalities using TSNE visualization. Each data point represents an embedding dimension. Red and blue circles denote unique features from modalities A and B, respectively, while red crosses and blue squares represent common features. The visualization clearly shows that common and unique features are distinctly separated in the embedding space, with common features being well overlapped between the two modalities. This separation and overlap are crucial for understanding the complementary information each modality provides. The figure is best viewed in color and zoomed in for detailed analysis. The DeCUR framework is designed as a multimodal extension of Barlow twins, focusing on self-supervised learning through redundancy reduction in a joint embedding space. This space is constructed from augmented views of inputs from both intramodal and cross-modal perspectives. A key aspect of DeCUR is the decoupling of common and unique representations across modalities. This is achieved by separating the total embedding dimension into common and unique parts, ensuring that common representations are identical and unique representations are decorrelated. Additionally, intramodal representation enhancement is introduced to prevent the collapse of unique dimensions and to boost the overall representation quality. Figure 2 illustrates the structure of DeCUR, a multimodal self-supervised learning method. It shows two modalities, M1 and M2, with each modality processing two augmented views through modality-specific encoders, E1, E2, and projectors, P1, P2, to produce embeddings C. The cross-modal embeddings are divided into common and unique dimensions, with the common dimensions correlation matrix optimized to be close to the identity matrix, and the unique dimensions correlation matrix optimized to be 0. Intramodal embeddings use both common and unique dimensions to calculate the correlation matrix, which is also optimized to be close to the identity matrix. DeCUR optionally incorporates deformable attention in the last layers of CONVNet encoders to enhance modality-specific feature learning. The DeCUR model is pre-trained using three distinct datasets, SSL4EOS12, GeoNRW, and SunRGBD. SSL4EOS12 provides 251,000 multimodal image pairs, GeoNRW offers 111,000 cropped patches, and SunRGBD includes 10,335 RGBD pairs. The model architecture features separate backbones for each modality, each equipped with a 3-layer MLP projector. Deformable attention is applied to enhance the ResNet 50 backbone. The optimization process follows specific protocols with varying epochs and batch sizes for different datasets, and the training is distributed across multiple GPUs, taking approximately 35 hours for SSL4 EOS12 and 6 hours each for GeoNRW and SunRGBD. Table 1 presents the transfer results of SAR optical models on Big EarthNet MM, focusing on multimodal, SAR only, and optical only tasks. The table reports mean average precision, MAP, scores under both linear probing and fine-tuning scenarios with 1% and 100% training labels. It also compares these results with state-of-the-art, SOTA, Earth Observation Foundation models. The scores highlight the performance of DeCUR, ours, against existing methods like SimCLR Cross, CLIP, Barlow Twins, and VICREG. Notably, DeCUR shows improvements in linear probing and fine-tuning with limited labels, demonstrating its effectiveness in self-supervised learning scenarios. The table also distinguishes between random initialization, RAND, init, and cross-modal approaches, providing a comprehensive view of the model's capabilities in various settings. The experimental results are evaluated across 3 key tasks: SAR optical scene classification, RGBDM semantic segmentation, and RGBDepth semantic segmentation. The evaluation is conducted under both full label and limited label settings, as well as in multimodal and single-modal scenarios. The primary metrics used for evaluation include mean average precision, MAP, for classification tasks, mean intersection over union, MIOU, for segmentation tasks, and overall accuracy, OA, for overall performance assessment. Table 2 presents the RGBDM transfer learning results, measured by mean intersection over union, MIOU, under both frozen encoder and full fine-tuning conditions on the GeoNRW dataset. The table is divided into multimodal, left, and RGB-only, right, sections. In the multimodal section, DeCUR demonstrates superior performance across all scenarios, outperforming other methods by a significant margin, up to 11.7% compared to SimCLR. Notably, DeCUR surpasses Barlow Twins and VICREG by at least 3% when fine-tuning with 1% labels. In the RGB-only section, DeCUR continues to show substantial improvement, leading by up to 12.1% over CLIP. Additionally, DeCUR outperforms single-modal Barlow Twins by 3.6% to 4.6% with a frozen encoder and by 1% to 3.1% in fine-tuning, highlighting the effectiveness of joint multimodal pre-training. Table 3 presents the fine-tuning results of RGBDepth encoders on the SunRGBD and NYU-Depth v2 datasets. The table shows that DeCUR significantly enhances the performance of FCN compared to CLIP, with an improvement of 4% in mean intersection over union, MIOU, on SunRGBD. Additionally, the use of DeCUR with the CMX model results in notable increases in MIOU, from 49.7% to 50.6% for CMX-B2 on SunRGBD, and from 56.9% to 57.3% for CMX-B5 on NYU-Depth v2. These results indicate that DeCUR effectively boosts the performance of both single-modal and multimodal models in semantic segmentation tasks. In the ablation studies on deformable attention, the residual deformable attention, RDA, module consistently improves performance across various scenarios, as highlighted in Table 4. Conversely, deformable attention, DA, without a residual connection shows a decrease in label-limited performance. Regarding the loss components, the ablation results in Table 5 indicate that intramodal training is crucial for maintaining stable performance. The absence of intramodal training leads to significant degradation in downstream tasks. The effectiveness of the DeCUR loss is affirmed through these studies, showing its importance in multimodal SSL. Additionally, the decoupling percentage study reveals that the best ratio of common dimensions is 87.5% for SAR optical and 75% for RGBDM, with performance changes smoothly along with the percentage of common dimensions. There is no significant performance drop even when decoupling up to 50% unique dimensions, indicating the sparsity of the common embedding space. Table 4 presents the ablation results focusing on the deformable attention (DA) module across various datasets. The results indicate that the residual deformable attention (RDA) consistently improves performance compared to the deformable attention without residual connection. For instance, on the BigEarthNet dataset at 1% label rate, the map without DA is 79.4, while with RDA it increases by plus 0.4. Similarly, on the BigEarthNet SR dataset at 1% label rate, the map improves from 38.4 to 38.8 with RDA. On the GeoNRWMM dataset at 100% label rate, the map improves from 78.3 to 79.5 with RDA. These findings highlight the effectiveness of the RDA module in enhancing the performance of the deformable attention mechanism. Table 5 presents the ablation results on the loss components of the DeCUR model, focusing on intramodal training and modality decoupling. The DeCUR model, which includes both intramodal training and modality decoupling, achieves the highest performance with 81.7% MAP and 36.9% MIOU. When neither intramodal nor modality-unique information is learned, without intra and DeCUR, the performance significantly degrades to 80.3% MAP and 33.6% MIOU. Conversely, when intramodal training is included but modality decoupling is excluded, without DeCUR, the model's performance improves to 81.1% MAP and 35.2% MIOU, indicating the complementary benefits of intramodal representations. These results underscore the effectiveness of the total DeCUR loss in enhancing model performance. Figure 3 presents ablation results, focusing on the percentage of common dimensions and the effect of the projector. The best percentage of common dimensions is identified as 87.5% for SAR optical and 75% for RGBDM, indicating more valid modality-unique information in orthophoto and elevation models. Interestingly, there is no significant performance drop even when decoupling up to 50% unique dimensions, suggesting the sparsity of the common embedding space. Additionally, DeCUR shows continuous improvement with increasing projector dimensionality, highlighting its effectiveness in enhancing representations. Figure 4 illustrates the ablation study on the decoupling percentage across different embedding dimensionalities. The left side of the figure focuses on the SR optical dataset, while the right side examines the RGBDM dataset. The study reveals that the optimal percentage of common dimensions remains consistent regardless of whether the embedding space is small or large. This consistency suggests a robust strategy for handling multimodal data across varying dimensionality settings. The explainability analysis of multimodal representations in DeCUR involves several key aspects. Firstly, cross-modal alignment is examined by calculating the alignment loss for each embedding dimension and comparing the results with Barlow twins. Secondly, deformable feature visualization highlights how different modalities focus on various aspects of the scene, such as ignoring clouds in optical images and focusing on them in SAR images. Lastly, spatial and spectral saliency statistics are analyzed using GradCM and integrated gradients, revealing the overlap and importance distribution of different bands. Figure 5 illustrates the cross-modal representation alignment on the left and the deformable attention (DA) visualization on the right. The cross-modal representation alignment shows how different modalities, such as optical and synthetic aperture radar (SAR) images, align their features to understand the same scene. The DA visualization, specifically in Part B, demonstrates the deformable points learned by the deformable attention module. These points highlight how each modality focuses on different aspects of the scene. Optical images learn to ignore clouds, while SAR images pay more attention to cloud regions as radar signals can penetrate them. This visualization also notes that the deformable points are more spread out compared to natural vision, due to the nature of satellite imagery and the constraints of the residual connection. Figure 6 presents spatial saliency statistics on the left and spectral saliency statistics on the right. The spatial saliency statistics, shown in Figure 6a, reveal that unique scores are more inclined towards 0 compared to common scores, indicating that modality-unique representations tend to be more orthogonal. This suggests that the interesting areas of modality-unique representations are less likely to overlap with common representations. On the other hand, Figure 6b illustrates spectral saliency statistics, confirming the significant influence of spectral information on optical unique representations. The band-wise importance distribution is consistent with domain knowledge, such as the importance of near-infrared bands and the lesser importance of atmospheric bands like water vapor and cirrus. DeCUR is a multimodal self-supervised learning method that aims to learn both cross-modal common and modality-unique representations. The method has been proven effective through extensive experiments in 3 common multimodal scenarios, highlighting the potential of modality decoupling. However, one limitation is the simplification of the multimodal situation by allocating the same common unique ratio across the dataset. Future work could address more complex scenarios where one modality may contain more unique information than the other in different scenes. Additionally, the grid search for the best percentage of common dimensions can be costly on a huge dataset, although a general percentage of around 80% can achieve reasonable performance. Future research could explore more efficient discovering strategies and adaptive decoupling strategies, as well as integrating modality decoupling in unified foundation models with more than 2 modalities. The research conducted by Y, Wang, C, Liu, and C. Albrecht was primarily funded by the Helmholtz Association through the Helmholtz AI Initiative, with a specific grant ID of ZTIPF 5-01. Additional computational support was provided by the Helmholtz Association's DeCUR at FZJ partition. The work of N. 8 Ali Braham received support from the European Commission under the Horizon 2020 Research and Innovation Program, specifically through the Eveland project. X. Zhu's work was supported by the German Federal Ministry of Education and Research within the AI4EO project, and by the Munich Center for Machine Learning. Z. Xiong's research was funded by the German Federal Ministry for the Environment, Nature Conservation, Nuclear Safety, and Consumer Protection. Lastly, Y. Wang's contributions to the rebuttal and final paper preparation were supported by the European Commission through the Thinking Earth project. Thank you for watching.